Hello students, welcome to EduSil. In this video, we are going to discuss about introduction of local search. So the content basically I am following the Tardo's book. Okay. So here, what are the local searches and how we can compare with the potential energy that we are going to discuss. And let us start with the introduction. It is written in the book as local search is a very general technique. It describes any algorithm that explores the space of possible solutions in a sequential fashion, moving in one step from a current solution to a nearby one that represents whenever we are finding a solution. Basically, we are working with the optimization of a solution. So once we are doing that one, once we are trying to get the optimal solution, so what exactly we are doing? We are starting from a sequential manner. Means if you start from one end, suppose there are many directions, or you can say to find an optimal solutions, we don't know where we have to stop. Suppose we are just starting towards B, then what exactly we are doing? We are doing in a sequential manner. Basically we are following in a sequential way. We have to follow from one end. This is what our fashion is. Means to whenever we are trying to find out the optimal solution, first we start from the initial position, but in a sequential means on a stepwise we have to follow that one, as well as what exactly we are going to do, like in a like nearby solutions means we have to follow the neighborhood. Okay, means what is there in to the neighborhood of the, like if you are getting the solution as suppose here you are getting 10, but nearest solution is 5, so definitely we will switch 5 rather than taking it 10. Next, if you are switching to 5, then we have to check the neighborhood. Neighborhood means immediate to that one. If it is 1, so we will be picking 1 instead of taking 5. This is what the neighborhood condition or nearby condition. Our fashion we have to follow is a sequential one. This is what the local search it represents. It's a definition. And in general, why we are getting, why we are using it, a very simple idea. Like we have read many design techniques. This is one of them where we are following a searching technique, a kind of searching technique, which is in general you can say it is a heuristic designed to find good but not necessarily optimal. We are not basically finding the purely optimal solution, but at least we are trying to get a good solution for a problem. Okay, whatever the problem that we have found out, or to get to the solution, we are not finding the optimal solution. Rather than getting the optimal solution, we are following a good solution for it. Okay, so it's also written as a solutions to a computational problem. What type of the problem that we have set as suppose computation problem. So we can begin by talking about what the search for the solution looks like at a global level. Means our target is basically when we are trying to search, there might be somewhere we are getting the optimal solution, but if you're not getting the original optimal solution, sometimes we are having, like, one here, but we might be stopped at 5 for certain reason. So for this case, we can say it is local to us. Don't worry, this just we started. I have certain examples for you to give you in detail. Although it's a detailed video, don't worry about that one. First, you focus like why we are saying it is local search. Why not global search? Okay. The meaning is like once we started, we somewhere suppose stick to 5. So this is what our local search. And we know out of these solutions we have like the values inside it, and we know the value is 1 here, which is a minimum out of all the values which we found, but we stop to that one, to the 5. This is what the local search means. Whenever we are searching, we stop somewhere, but you cannot move ahead because of certain reason. This is what the local search is. Means we just immediately search this one, but we are not picking with the global solution, which is named as this global search. You can say the minimize. Basically, we can say the minimum one is a global minimum for us, is a local minimum for us. Okay, So whatever the local minimum we are finding out, so within the search we are just saying it is a local search. So global minimum means out of all the solutions which we have a minimum which is a less among all the minimums, but the problem is we are not reaching to that one, which is a global minimum. Global minimum is considered as the optimal solution here, but we are not getting that one. But at least out of the solutions which we started from a sequential manner, at least we are getting the good one. This is what a local search means. Okay, so I have to clear about the definition. Now we are going to some more idea, like as it is there in our 12.1 in the book, like landscape of optimization problem, how it look like. Okay, so basically it is ask the people thinking in terms of analogy with the physics, as might be you have read in the physics about the energy. Okay, like mechanical energy. I'm just writing insert mechanical energy. Basically it has two different kind of energies are included, which is potential energy, another is kinetic energy. Okay, as you have already read about this one, so I'm just reminding this one once again. Okay, potential energy is certain energy where we, suppose it's a height, like you just think about you are climbing on a hill. This is a hill. Okay, so you are just having one vehicle, so you are going towards the top of the hill. Suppose you reached here. Okay, suppose you reached here in the just the top of the position. Now what you have to do, this is what the uh, the you can say it's stop there, and without any starting of the vehicle you can start moving towards the down. Clear? You can move from top to down without starting of the engine. This is what in general we have seen. So the height it matters. If more the height, the more the distance you cover without starting the engine. Clear? This is what exactly the potential energy. It whenever it reaches to a height, whenever it reaches to a height, so height I'm just representing as h. More the height, more the potential energy we are gaining. How? The potential energy is, again I must tell you, there are again two categories. One is, you know, gravitational one, another is elasticity or elastic, you can say, potential energy. Through, like, if you are compressing a spring, that is what you are just compressing. It means you are focusing on the configuration of that body. If you are just changing the position of the body, like you are just position in the sense like height, so it's a gravitational one which you are indirectly consuming. Okay, so this is what, based on the height. Okay, based on the height, if you're increasing the height, definitely the energy is exactly consumed by the body. So why we are reading that, I'll tell you, but it's a part of physics. So first we'll let know exactly what the physics. Okay, where how you are going to use that one. Suppose a hill that you just climbed there, on the just top of it. So what you have to do, like, you just stop the engine and you just let it a free move. The vehicle which you are actually riding just have a free move there. So based on the height, so when it start moving from the top of the hill towards the bottom of the hill, so it converts the potential energy to kinetic energy. Here it is potential energy when it reaches to the top. When it goes down, so it converts to the kinetic energy. And the potential energy is high at this moment. It is high, but when it reaches to this, suppose this is our land, when it reaches the potential energy, I'm just writing this one as this one. The potential energy here is low. Here is low. Means we are reaching the ground. There is no such height. We cannot measure with the height directly, because from the ground level we are measuring that one. So when it reaches towards the ground, we are saying the potential energy is low. In this way, basically, we are following the optimization problem, local search basically. Okay. So how do we compare then? The same thing it is written as a hockey pucks like what they have just taken as a mass m and the height is h. In general, whenever we are focusing on the potential energy, it is mass, gravitational force, and height. This is for the potential energies equation. Okay, and there is like if you are focusing on the kinetic energy, it is half of v square. V represents the velocity because you are consuming that one while you are just in a motion. So potential energy is based on the configuration as well as the position of the body. We are not in a motion. So but the kinetic energy, when there is a motion, kinetic energy is there. So here our target is not about the kinetic energy. Our target is about the potential energy. Let us think like we started to search, we are at this position, we are starting to search the optimal one. Okay, the local search, the optimal is this one. So whenever we start searching this from this one, so we start searching it and we stopped here. The algorithm is stopped here because we reaches at the end of it. So this is what we can say is our potential energy is less at this point, so we stopped. This is why we are using the concept of potential energy. Otherwise we didn't have this one. Okay, we don't want to use this one. We are just watching it like how the local sets is exactly working. That's why we are introducing physics here. Okay, like as all of you have read it, so that's why we're just reminding those one and we are just using this. So next, this structure we can say are called as a funnel, okay, which is written here also, funnel funnel. If you are getting a single one, a single type of funnel, so you can say it's a single funnel or a simple funnel. If you see this two type of creep in it, so you can say this is called as dual funnel or double funnel. Okay. So I'm just highlighting here also underlining this one, double funnel, or sometimes we are saying it is simple or single funnel. So whenever you have a single or simple funnel, we can say when a potential energy landscape has structure for this potential is easy to find the lowest point. Means whenever we start searching, so here the optimal we are getting, so no need to worry. We stopped here and we found this is the minimum one. So to find the minimum or optimal answer, we can search from one end in a sequential order and we restart here. But whenever we are just focusing with the double funnel, so if you started from this, as you know why we are using potential energy, I'm saying. Suppose you started from this end, so as for the potential energy, you can stop here as well as the kinetic energy is there, so you can cross there. But if you started from C, so definitely your value will be stopped at here because you maximum think up to this. That's why we are using the potential energy concept. Like whether we can cross it to A or not. That is what we are exactly discussing earlier in this one. In some cases we can stop there. So what exactly it is? So in the basis of potential energy we are trying to understand. Suppose we started here and we max to max the kinetic energy which we got or which we gained maximum in this case because we started here. If you the more the height, the more the kinetic energy will definitely apply in future because the potential energy higher, so definitely that will be converted to kinetic energy and that kinetic energy will lead you to cross over anywhere. Okay, so it started from the sea. From the sea definitely you cannot cross this barrier. This is a barrier basically. Okay, so you stopped here and you say no, we reached the minimum one. This minimum is called as local minimum, or you can say a local search you did, but the global minimum is this one. You are not reaching this global minimum, you are just stick to the local minimum. Okay, this is what it is written here. You can read like figure 2.2, it says A is a lower than the B point, so more desirable places like which I told you, like there is a ball. Suppose you started with the ball that came to rest, but if we start the roll from point C, it will not be able to get over the barrier between two funnels, which I told you earlier, like when height is less, so that's why we can expect up to that one. We cannot say like it will be beyond that one. So it says like we will end up with B, and we say the ball has a local minimum. This is what our, instead of reaching, like we cannot reach to or the barrier which is getting here. So we stay here. This is what our local minimum. We started in a sequential order, but we stopped there because of certain, you can say the searches which we have done based on the potential energy. We cannot cross over that one. Clear? But we are missing the global minimum because of this reason, because we started at C, so that's why we cannot cross over that one and we stopped this. I hope you clearly understood like how potential energy is exactly correlating with the finding the local search. Next figure is like if you are having such type of spikes, or you can say such types of funnels, like more number of funnels or more number of spikes are there. So what you can say, instead of saying it is simple or single or might be a double, so you can say it is jagged funnel. So jagged funnel, what exactly you can say, there are many barriers to reach at global minimum. So you may not reach to this one, might be you have many barriers to cross over. There are certain problems or difficulties that we are finding out from this jagged funnel to reach the global minimum. That's why we have lot many different algorithms to reach this minimum. Okay, this is how we are just using the potential energy to show like how we are reaching to a searches or might be reaching to a minimum point using this sequential order or following the sequential order as well as neighboring concept. So I just kept the summary of it like with the definition as it is there in a PPT of the Tados book. So here the local search is algorithm that explores the space of possible solutions. Means there are many possible solutions which are spike, you can say the possible solutions for us in sequential fashion. We can start from one end, means we will not skip any step and we will be reaching towards the global minimum, moving from the current solutions to nearby one. This nearby one is neighborhood condition or neighborhood relation that we are just reading. The next line, neighbor relation is like S to S dash be a neighbor relation for a problem. Means what is S dash, what is S, then we are going to discuss. A gradient descent is a concept, you can say it's a word that is getting used here. Like let's S denotes a current solution. Okay, like you have a certain solution. Suppose like you just reached this one, this is your solution. The next solution is this one. So you, what you have to do, like gradient descent, basically if there is a neighbor solution which is S dash of S with a strictly lower than cost. Like what are the costs that you have? Current cost is suppose lower than the the neighbor cost, so you need not to switch it. If you have the current cost is 10, as I told you earlier in the first slide, if your current cost is this one, so the next which is neighbor to it is considered as this one is 5. So what you have to do, like you replace S with the neighbor whose cost is small as possible. So you can switch, like the current cost will be the next clause, or so neighbor cost will be the current cost. Otherwise if this is not be like this, so we terminate the algorithm and we said suppose if this is a condition we can exchange. I'm just saying it is exchange if you are having the current cost as 5 and the neighbor cost is 10, so you have to terminate. This is what you have to do, terminate. Means you have reached your current position. This is what it says. So in this way, what we are getting might be somewhere we stopped, somewhere we are trying to reach to the global minimum. In this jagged funnel, this is our global minimum. Here, a simple funnel we are having, so which is easy for us to reach to the global minimum using this neighbor relation as well as the local search concept, or you can say it's a gradient descent basically we're following to get the local search. I hope you clearly understood this one, introduction of this local search and the potential energy, basically how we can define that one while finding this. Okay, so now we are trying to connect the optimization as I told you, like how we are getting it. The same thing it is written here, like the cost, the possible solutions is just represented as a capital C, where we are representing the cost as this one, which I recently discussed with you. The finding the solutions, you can say it's a optimized solutions for us. So how do we find? Like we have to follow the neighbor relation. Basically neighbor relation, whenever we are finding just the current selections which you have done with the next neighbor solution will be, you can add something to it or you can delete something to it. Whenever I'm saying s dash, in that case we are adding something or we can deleting something, adding or deleting, then only we can say we are having a neighbor to it. Okay, so neighbor condition or neighbor relation is very much helpful here while finding the optimal solution that we have seen here. So this is what it is written. So neighborhood, basically we are following this concept. Next one, based on this we are finding the solution sequential manner. So local search algorithm takes this setup, which the setup like we said, including neighbor relation, and work according to the following high level scheme. Okay, based on that we are maintaining it, and based on maintaining this one, so we are trying to get a perfect solution. Not if you are not getting the optimal solutions, it's quite good solution you are expecting using the local search. I hope it is clearly understood by you. If any doubt you are facing, kindly comment below. Have a good day.